Okay. Looks like we are ready to go. So, well, there we go. Atomic mass. All right. So last time we talked about atomic symbology and things like that, and I mentioned atomic mass, where atomic mass is a measure of the mass. Okay. So just to reiterate, atomic mass is not mass number. Mass number is a precise count of protons and neutrons. Therefore, it's always going to be a perfectly whole number. You cannot have half a proton or half a neutron. The atomic mass is the actual mass of the atom. And it's usually going to be measured in atomic mass units, abbreviated AMU. And it's almost always going to represent an average of all the different atoms out there. And it's never ever going to be a whole number. Now, it doesn't always have to be an average. We might be talking about a particular isotope. But in the vast majority of the chemistry we're going to do in this class, we're going to be talking about just averages, huge numbers of randomly collected atoms. So, how do you like these apples? This is how we talk about averages for this sort of thing. Imagine you have 10 apples. What is the average mass of your apples? Averages are rather straightforward when you're looking at a small number of things. You just add up all the numbers, divide by however many you have. Okay, so getting fancy, you add up, this is the Greek letter sigma, capital sigma. You add up the masses of the individual apples, you divide by the total number of apples. Okay? So 5 plus 7 plus 8 plus 4 plus 6 plus 6 plus 5 plus 7 plus 4.5 plus 8.5 divided by 10. 61 divided by 10 is 6.1 grams per apple. The average mass of these 10 apples is 6.1 grams. But what if you have millions of apples? You can't go in and measure all of the apples because that would take prohibitively long. So instead, we take a sample. Okay, we just grab 100 apples at random. Okay, if you are good at what you're doing, then this is what's called a representative sample. Because they're random, you can assume that they look like the total, all of the apples. Okay, so you grab 100 apples at random. 12 of them have 4.5 grams. 18 are 5 grams. 27 are 6 grams. 10 are 6.5 grams. 13 are 7 grams, 9 are 8 grams, 7 are 8.5 grams, 4 are 9 grams. So for those 100 apples, you do the same thing. You have 12 apples at 4.5 grams, 18 at 5 grams, 27 at 6 grams, and so on. You just add them all up, divide by 100 because you have 100 apples, and your average is 6.3 grams per apple. Notice I rounded because of significant figures. You should have covered that in lab of this week. Okay, so that is a statistical sample. Now, the thing is, 100 apples isn't particularly great. In terms of statistics, you really want several hundred, maybe about 500 apples. I can't remember the exact numbers, but 500 gets you decent. Now, the thing is, we're not actually talking about apples, we're talking about atoms. Okay? So iron has dozens of isotopes, but only 4 that occur in measurable quantities in nature. And instead of looking at exactly 100 atoms, we just use percentages. Okay? So using synchrotrons and other nuclear devices, they're able to separate the isotopes and gather the percentages for how many atoms there are of each isotope. Okay? So of the iron atoms you find in nature, on the surface of the Earth, a little less than 6% are going to be iron 54. The majority, a little less than 92%, are iron 56. A little over 2% are iron 57, and then a very small amount are iron 58. Okay? So every atom of iron has 26 protons. That's this first column here. And then we have varying numbers of neutrons depending on the isotope. So iron 54 has 28 neutrons. Iron 56 has 30 neutrons. Iron 57 has 31 neutrons. Iron 58 has 32 neutrons. Some of you might be asking, what happened to iron 55? There is no iron 55. Nuclear physics is basically a combination of black magic and physics. It gets really, really weird. Some nuclei, some combinations of protons and neutrons are just unstable, and you just don't find them in nature. So iron 55 is not a thing. It just doesn't happen because it's just weirdly unstable. When you look at isotopes, you'll find that most of them are even numbers. It's just weird. It's just the way things are. All right. And because of the black magic, iron 56 is way more stable than iron 54, which is a little bit more stable than iron 57, which is more stable than iron 58. It's just the way things are. Okay. So we have our percentages, and we have our masses. Okay. So iron 54, we have our protons, we have our neutrons, giving us 54.431796 atomic mass units for one atom of iron 54. So we do that for all four of our isotopes. Iron 56 is 56.44, iron 57 is 57.45, iron 58 is 58.46. Huzzah. Okay. Now, we can treat this an awful lot like we did the apples. Okay. Except instead of 100 apples, we have 100 atoms. That's what percent means. Literally, it means per 100. Okay. So for every 100 atoms of iron 54, 5.84535 of those atoms will have a mass of 54.431796. Okay. For every 100 atoms, a little less than 92 of them will be iron 56, and so on. That's how percentages work. Okay. So percentage does half the work of averaging for you. Okay. Percent means per 100, so you're basically already built in dividing by 100. So 54.43 atomic mass units times our 5.84535%. 56 times 91%. 57 times 2%. 58 times 0.2%. Okay. You do that multiplication, you add them all together, and then you divide by 100 because it's percent per 100. When you do that, you get 56.3590 atomic mass units, which is not great. The actual atomic mass of iron is 55.845 atomic mass units. What went wrong? Well, it's because I was doing the math weird. Okay, it's because of how neutrons work as glue. When you're looking at the sort of glue that you used on construction paper back in elementary school, Elmer's glue works by filling in the cracks on two surfaces, and then it dries, and the remaining stuff, it just sort of sticks the two things together. Neutrons can't do that. Instead, they use the strong nuclear force. And the energy to hold things together has to come from somewhere. And in this case, it comes from Einstein. Specifically, E equals mc squared. Okay, mass is energy, energy is mass. The two are the same thing. So in order for neutrons to hold the nucleus together, they turn some of their mass into energy. So when we look at the actual masses of the isotopes, these numbers that I got by adding up the individual masses of the protons and neutrons is wrong. Okay, those numbers have to be decreased in order to glue the nuclei together. Okay, so here's the masses that I calculated right here. Here's the actual masses of those isotopes. You notice that they are significantly different, from 54.43 down to 53.94. 56.45 down to 55.93. Okay, so there's a significant difference for each one. Okay? In other words, when you have to do this sort of math, and you will have to do this sort of math on the test, they're not expecting you to add up the masses of the individual protons and neutrons. They'll give you the masses of the individual isotopes. So then you take those masses that they give you, the actual masses of the isotopes, you multiply them by the percentages, you add them together, you divide by 100, and you get 54.8458, which is much, much closer to the actual mass of the whatchamacallit. Oh, come on. Play. There we go. Oh, before... okay. This is from the game Prince of Persia, The Two Thrones. Getting kind of dated now. But this guy with the glowy arm, he is sort of possessed by a demon, and that's the one making the sarcastic comments. He also spent several years being chased by a different demon, and thus he's slowly learning how to be a decent person again from the girl on the left, on the right, his left.
What is your favorite color?
Color?
Shall I repeat the question?
Blue. Blue? That's not my favorite color. What is the point of this?
Must every conversation we have be so serious? I know so little about you.
Very well. Then, what is your favorite food?
A pomegranate, of course.
I do not like pomegranates.
What is wrong with you?
They are messy, impossible to eat with dignity. So much work for a few seeds.
But is it not the effort that makes them that much sweeter?
I think I'm going to be sick.
Okay, so doing a lot of work here in order to find these atomic masses. And it's not absolutely necessary. So iron 54, the actual mass of iron 54 is this 53.9396. That's really close to 54. Okay. Likewise, iron 56, 55.93 is really close to 56. Iron 57, 56.94, really close to 57, right? So for the most part, unless you have to be really, really close, you can just use the mass number. It will be close enough. I mean, you'll be off by like 3-4%, which isn't great. In fact, that's not good enough for most government or industry applications, but it's decent if you're not having to be too careful. So you can just take the mass number, multiply by the percentage, add it up, divide by 100, and here we get doing that 55.911. Which, remember, the actual mass of iron is 55.845. It's not terrible. Not perfect, not terrible. So, if you're not using a specific isotope, go ahead and use the mass off the periodic table. Mass on the periodic table, like for iron, 55.845. For oxygen, 15.999. If you are using a particular isotope, you're going to have to find the mass of that particular isotope, unless it's given to you. And if you're calculating an atomic mass from relative abundance, on the test, they'll probably give you the atomic masses for each isotope. If not, just go ahead and use the mass number. Okay. If they give you the masses, use the masses. Otherwise, just go ahead and use the mass number. It'll be a little bit off, but not terribly. Okay. If you have the periodic table, go ahead and use the mass on the periodic table. So, here is an example. What is the mass of this random element, not a real thing, XP, Xepatanium, with masses 92, 94, 95, 96, and 98. And these relative abundances here on the right. Okay. Let's see. I will go ahead and play some amusing music for you while you work on that.
Here we go.
All right, that's enough of that. Okay, so that is the mass of Xepatanium. Notice that when I did the multiplication here in the middle, instead of multiplying by 12.873, I multiplied by 0.12873. A percentage, although we report it as a number between 0 and 100, it's actually a fraction, a number between 0 and 1. So 50% is actually 0.5. It's saying that half of the stuff is the thing, right? So when I did it like this, just moving the decimal place 2 to the left, I basically pre-divided by 100. You don't have to do it that way. It's just something that I have gotten used to, and I don't recall. It's been a while since I made these slides. I might have just done that automatically while making this. But that is, so you could do 92 times 0.12 and get these numbers added together, or you can do 92 times 12.873 and then add the numbers together, divide by 100. You'll get the same answer either way. When you're doing an average, your number had better end up somewhere in between the maximum and the minimum. Otherwise, that means you've screwed up somewhere. So here is a more difficult kind of problem. Oops. There are two isotopes of chlorine, chlorine-35 and chlorine-37. What are their relative abundances? Okay. Here I give you the atomic mass of each isotope. So 34.969 for chlorine-35. 36.966 for chlorine-37, and then I give you the measured average of chlorine, 35.453. What are the relative abundances of chlorine-35 and chlorine-37? This might look like an impossible problem to solve, but it's not. You do have enough information here. Okay, the first time I did this, I set this up, put it in the slides, and then 2 weeks later, this was an actual problem on the test. So that's just the way of saying this is a sort of popular kind of thing. When they do tests, they like to take a problem that you already know how to do and they throw it at you sideways or upside down or something to see if you really understand what you're doing. That's why it's a good idea to study rather than relying on your ability to memorize certain kinds of problems. So here's how we solve this. We have our two isotopes. Okay, so chlorine-35 has a mass of 34.969, and then it has some relative abundance, a percentage A. Then we have chlorine-37 with a mass of 36.966, and it has some abundance B. Divide by 100. And they add up to 35.453. Okay. So that is one set of facts that we know. But we have one equation, we have two unknowns. We cannot solve what we have yet. However, there is another piece of information that I gave you. Okay. Look back at the problem. There are only two isotopes of chlorine. So the percentage of chlorine-35 plus the percentage of chlorine-37 has to be 100%. Those are the only two that there are. So that is how we can solve this. We have two unknowns, we have two equations. Now I'm going to go ahead and simplify this a little bit just to save us from having to do too much math. I'm going to get rid of the dividing by 100, and instead of 100, A plus B is equal to 1. Makes it just a little bit easier. Okay. So what we do now is A is equal to 1 minus B. We just subtract B from both sides. And now we take this, and we plug it in up here for A. So 34.969 times 1 minus B plus 36.966B is equal to 35.453. Now, the only variable we have is B. Okay. Just a quick reminder, B is the percentage of chlorine-37. So now we solve for B. We multiply this through to both of those. We get 34.969 minus 34.969b plus 36.966b is equal to 35.453. I apologize for the way my writing is wandering over the page. I'm kind of writing at a weird angle here. Hopefully my new computer desk will arrive tomorrow. All right. So now we can collect these two terms, 36.966 minus 34.969, because we have a positive there, a negative there, is going to be, I'll go ahead and use a calculator for this. $36.966. 36.966 minus 34.969. 36.966 minus 34.969. Okay, now we just go ahead and subtract 34.969 from both sides. It's going to give us 1.997b is equal to 0.484. Now we divide both sides by 1.997. B is equal to 0.242. What does that mean? Remember, B is the percentage of chlorine 37. And because I already went through and divided by 100 and everything, that means that out of all the chlorine in the universe, or on Earth, I should say, 24.2% is chlorine 37, which means that the remainder, 75.8%, is chlorine 35. Now, real quick, we can do a double check to see if this makes sense. Does it make sense for the majority of the chlorine out there to be chlorine 35? Well, let's go ahead and look at the average. The average of our chlorine, written it down multiple times, 35.453. Okay. That means that the average is really close to 35. It's a lot further from 37, which means most of the chlorine out there is, in fact, chlorine 35. So this answer does make sense given the information we had. No real error there. All right. So, moving on from masses of individual atoms, let's look at masses of compounds. So, there are various terms we use. We tend to use them kind of interchangeably. Technically, they have different meanings. So, molecular mass is the mass of a molecule. Formula mass, if we're looking at something that's not a molecule, meaning an ionic compound like table salt. So, because they don't have molecules, but they do have formulas. So we talk about the mass of the formula. Molar mass, that's something that we'll get to later. Okay, so we use these terms kind of interchangeably. They're not technically the same thing. Molecular mass, formula mass, and molar mass. I will try to use molar mass for the most part. We'll get into what that means in the next lecture. Okay. So, to find the mass of a compound, no matter what kind of compound you're talking about, you just add up the masses of all the individual atoms. Okay? So you take them off the periodic table and you add them up. Okay. So let us, for example, carbon dioxide. Carbon dioxide is one atom of carbon bound to 2 atoms of oxygen. Okay? That's how you get one molecule of CO2. So you look at the periodic table, Okay. Carbon has an average atomic mass of 12.011. Oxygen has an average atomic mass of 15.999. Okay. Unless they tell you that you're looking at particular isotopes, you just grab the mass right off the periodic table. There's no reason to assume a particular isotope. You're just going for an average kind of atom. So you add those up. 1 atom of carbon plus 2 atoms of oxygen is going to be 44.009 atomic mass units. That is the molecular mass or molar mass of carbon dioxide. 1 molecule of carbon dioxide, on average, is 44.009 atomic mass units. Sugar is a little bit bigger. Sugar is 6 atoms of carbon, 12 atoms of hydrogen, 6 atoms of oxygen. Well, specifically, this is glucose. Sugar is kind of a catch-all term. So the mass of carbon, again, right at the periodic table, is 12.011. Hydrogen is 1.0078. Oxygen, 15.999. So 12.011 times 6 is 72.066. 1.0078 times 12 is 12.094. 15.999 times 6 is 95.994. And then you add those 3 numbers together, and the molecular mass of sugar is 180.154 atomic mass units. So if you have just random atoms of carbon, hydrogen, and oxygen, then the typical molecule of glucose is going to have an atomic mass of 180.154. Okay. So just generally, for a random compound, you just take the subscript, the number of atoms, multiply it by the mass of that atom. Do that for each of the atoms, you add them together, and that gets you the formula mass or molecular mass or molar mass. Okay, the mass of the molecule, the mass of the compound. Okay. So go ahead and take a minute or two to work out the mass of nicotine, C10H14N2. Let's see. Here's some music.
Where can you see light?
Okay, you can't hear that yet because I still have to change the thing. Oh no, it'll still work.
Only in Kenya. Come to Kenya, we've got lions. Where can you see tigers? Only in Kenya. Got lions and tigers only in Kenya. Forget Norway. Kenya. Oh, Kenya. Where the giraffes are. And the zebra. Kenya. 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 Going to Kenya. Can you believe it?
All right. So that is nicotine. 12.011 times 10, 120. Blah, 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 blah. Okay. So, I mean, this is not particularly difficult math. When doing this on the test, you don't have to draw up a full table like this. I recommend it just as a way to keep track of everything because you're going to be looking at, half a dozen numbers and you can lose track of things in your calculator. You might slip a decimal place. You never know. It's not a terrible idea to write everything down. But the molecular mass of nicotine is 162.23 atomic mass units. Okay. So why do we care about this? Chemists work with atoms, but obviously not individual atoms because they're incredibly ridiculously small. So we need to be able to figure out how much of something we have and a certain mass of the thing. Okay. And the reason we have to make that distinction is because the mass is how much matter is present, not how many atoms are present. Going back over to the periodic table, a single atom of hydrogen is going to have a mass of 1.008 atomic mass units. A single atom of oxygen is 15.999 atomic mass units. So very different masses for the same number of atoms. So that's why we have come up with a way to be able to find the relationship between mass and the number of, well, speaking generally, particles. Not just the number of atoms, but could be the number of molecules and so on. So that is what we will talk about in the next